job by adding reflective flakes to it. In fact, as we look at the controls over in the attribute editor, we can see that we do indeed have a whole rollout dedicated to tweaking and controlling flakes. At this moment in time, we see that the reflect value for them is set at 0, meaning they are currently set to be essentially invisible. Well, let's make our flakes very visible in the render by setting the reflect value to 0.75, and then, after jumping into our close-up camera view, taking another render. Right away we can see that because our geometry has been created as an accurately scaled toy car, the material, which of course has been designed by default for use with life-sized vehicles, is making our flakes look way too big. We can easily scale these down though by means of the aptly named flake scale parameter. Let's do that, setting the value here to 0.006. Now the intensity of the reflections is probably a little too bright here, so let's drop the reflect value back down to a value of 0.6, and also perhaps blend the flakes a little more by altering the flake weight parameter, setting it to around about 0.65. At this scale we will probably also be getting a few too many flakes, so let's drop the density parameter to 0.2, keeping in mind that the scale difference now makes this parameter quite sensitive. Let's also take another render just to be certain that we are happy with what we have so far. Another aspect of the car paint material that we will probably always want to tweak would be its reflectivity levels. Different types of vehicle finishes produce very different reflection looks, and to help recreate those, the car paint phenomenon gives us both specular and true reflection controls. We can again, as with the MIA material, completely disable the specular component by setting the specular weight parameter here to a value of 0, noting how that change clearly updates the look of our material in the preview. One thing perhaps that is not quite so immediately apparent when we first look at the car paint phenomenon's true reflection controls is the fact that they do indeed work in a very similar manner to those found on the MIA material itself. You will perhaps recall from earlier exercises that in the BRDF section on the MIA material we have 0 and 90-degree angle controls, with 0 controlling the reflection level of faces looking directly into the rendering camera, whilst the 90-degree value determines the reflectivity levels of faces sitting at a right angle to it. Well, in the car paint material, the reflection base weight control takes care of 0-degree angle reflectivity, whilst reflection edge weight corresponds to 90-degree angle control, with the edge factor performing much the same function as the BRDF interpolation curve. That is, it determines how sharp or how gradual the transition between the two reflection values will be. To demonstrate the similarity between these and the MIA material controls, let's set the diffuse colours in this material to black, set the reflection base weight value to 0.9 and the edge factor to 0.5. What this gives us, as you can see in the preview, is a pretty accurate recreation of the clean looking chrome material that we created earlier in this chapter. Not that this is what we're really wanting to do here, so let's set those options back as they were by using the undo command a few times, and then we can move on to our next video where we will continue to explore more of the MI car paint phenomenon's controls. Having already seen how a number of options on the car paint phenomenon work, let's continue our examination of it by taking a look at how we can add blurred reflection effects to it. We have already noted that the true reflection controls on the material work in a manner almost identical to those found on the MIA material, using facing and edge or 0 and 90-degree angle controls. The reflection glossiness controls, however, work a little differently. With the glossiness spread and samples values set to 0, we get completely glossy or polished reflections as one dictionary defines the word glossy. If I were to dramatically increase the glossiness spread, however, let's say something like 0.5, we would in fact still get no change in the look of our reflections. This is because in order to bring the glossiness spread parameter into play, we need to specify the samples value to be used. So if I go ahead and set that option to something like 8 and take a render, we can see that what we get now are very diffused or non-glossy reflections in the material. These are heading in fact towards a matte look finish to our car paint. Let's reset those controls to 0 so that we can get back to purely glossy reflections. One of the really interesting controls found on the car paint material is the ability it gives us to create a completely separate edge colour. To see how this works, let's jump back into our main camera view, and in the edge colour control found in the material's diffuse rollout, switch to something that will show up very obviously in a render, such as a nice bright green. We can tighten or push that colour more towards geometry edges if we like by setting the edge colour bias to something like 0.25. When we take a render now, we can clearly see what this parameter has done, which is to create these blended bright green edges wherever a surface starts to turn away from the rendering camera and head towards that 90-degree angle threshold. Another nice feature of the colour controls, if I again just reset those changes, is the fact that besides setting up individual base and lit colours, with lit being the colour brought out by direct light hitting the surface, we also have the ability to set different weights and biases for them. The lit colour bias, for instance, if I now set the lit colour to show up as a bright green, spreads the lit colour itself across the surface of our geometry. In fact, if I just come down to the reflection controls, and for the time being set both weight parameters here to 0, we can much more clearly in our preview see just what the colour components here are doing. So at a really low bias value of 0.001, we see our lit colour spread quite a bit, affecting quite a number of surface polygons. Whereas at a value of 20, we see the colour become restricted to a very tight area on the geometry surface. The controls for the collective diffuse components, by way of contrast, give us both weight and bias options, with weight essentially giving us the ability to dial colour values up or down. A value of 1 means no adjustment has been applied, 0 removes colour contribution altogether, whilst anything above 1 multiplies colour values in the material. Diffuse bias, on the other hand, rather than dealing with or controlling colour values, deals instead with the fall-off of diffuse shading. At a value of 1, the material becomes Lambertian in nature, that is, a perfectly diffuse surface, whilst higher values push the diffuse peak towards the light source, producing a more metallic look. Recommended usable values here are between 0.5 and 2, with 1.5 being the default. Now, as if all of the control highlighted over the past two videos wasn't enough, you will have noticed that pretty much every single parameter in the car paint phenomenon can be controlled by means of map types, meaning that although the material itself has been designed with a very specific use in mind, that of creating vehicle finishes, the possibilities for endless material variations within that look becomes almost limitless. Although NVIDIA's MILA or Mila material has been around for a while now and is most definitely the direction in which all material development for NVIDIA render engines is going, it is for some still new enough to have a number of kinks in the workflow that need ironing out before it gets adopted into their everyday pipeline. Now, don't get me wrong, lots of artists are very successfully making use of the Mila material and its powerful feature set in production right now. Many of these artists, though, tend to be pretty experienced at dealing with render engine quirks and are adept at working around the little glitches that pop up from time to time. That having been said, though, a quick look over the course of the next two videos at the basic workings of the Mila material would certainly seem to be appropriate for our up and running with Mental Ray course. The first thing we will need to grasp then is that the Mila material works quite a bit differently from any of Mental Ray's other main material types. Where the MIA material is a monolithic shader designed to have every feature you might need right there at your fingertips, the Mila material takes a much more efficient add it as and when you need it approach. To take a look at how it does this, let's open up the Hypershade window and from the Mental Ray material section add a new Mila material to the work area. What we get by default is a very basic and easy to work with set of controls that consist of a base component set to diffuse from the drop-down, a colour option that has swatch and map controls, and a roughness slider. Now, dependent upon which of the base component types we choose from the drop-down here, these basic options can and will change. However, the three additional roll-ups that we see here, contribution, material properties, and extra attributes, are always available no matter which base component we choose. Contribution, if we just open that up, gives us the ability to control how much the direct and indirect lighting in the scene will affect this particular material at render time. To demonstrate how this works, let's go ahead and select and hide all of the objects on our shelf here, and then take a quick render of the scene. Now, of course, because we are again using cached Final Gather and Photon Map files, we can still see the occlusion shadows for the hidden geometry, but still, let's jump into Hypershade and select the Mila material that is currently applied to the shelf geometry. This, as you can see in the attribute editor, has the same basic diffuse controls that we have already looked at, only this time of course the colour information is being supplied by an image file. We also see the three additional rollouts that we highlighted a moment or two ago. Going back to the contribution rollout then, let's see what happens if we set the direct light contribution value to 0, the indirect contribution at 2, and then take a region render that encompasses both the wall and shelf geometries. Well, whilst the wall, as we would expect, has clearly remained unchanged, the shelf material now has a much warmer, more saturated look to it due to the fact that direct light contribution has now been removed. Let's see what happens if we switch things around and this time set the direct light contribution to a value of 2 and indirect lighting to 0. Well, this time of course we get a much brighter direct lighting pass, one that is clearly much cooler in colour tone than the indirect lighting. This is because our direct light here is coming from the Mental Ray Sky portals, which of course are pulling their colour information from the physical sky environment shader. With the Mila material then, we get the ability to perform basic but still very quick and powerful scene relighting without actually touching any of the lights in the scene at all. We also have here in the Material Properties rollout the ability to control the opacity of a material once it has been applied to an object, with a value of 1 making it completely visible, whilst a value of 0 of course makes it completely invisible. The map slot gives us a cutout opacity control, meaning we can use a grayscale control map to either add or subtract opacity to and from very specific areas of the material. If we find ourselves needing to make a transparent material that is non-refractive, whilst at the same time still keeping all of the reflectivity properties intact, then we also have a thin-walled option that we can take advantage of. Now, as good as all of these auxiliary controls are in terms of adding special features to the material, what about controlling the main properties of the material itself? How do we go about doing that? Well, let's move on to our next exercise where we can take a look at using the Mila material to recreate the basic diffuse, refractive and reflective materials that we have already looked at earlier in this chapter. In this particular exercise, we want to explore, at least to some extent, the basic way in which the Mila material works, specifically by recreating the three basic materials that we have already looked at in this chapter whilst using the MIA Material X shader, namely wood, glass and metal. To get started, let's recreate our shelf's diffuse material by opening up the Hypershade window and then adding a new Mila material to the work area, naming it Mila_shelf_diffuse. We then of course need to select the shelf geometry in the viewport and apply the new material to it. Now, one drawback with Mila materials is that they don't currently provide any feedback in the Maya viewport, not even basic diffuse colour information. We currently get visual feedback only in the material preview swatch. Now, of course, rather than working with just a straight colour here, we want to apply a diffuse colour map, specifically a photograph of wood. So let's go ahead and do that by clicking on the Create Render Node button for the colour option, from the browser grabbing a file node, and then adding the kitchen_cupboardwood_diffuse.jpg to the file slot, being sure to take a render once we're done. And as simply as that, we have created our first Mila-based diffuse material. Of course, if we look at the base component drop-down, we see that there are in fact quite a number of pre-made phenomenon options for the material base that we could have chosen from. So basic subsurface scattering and translucency, as well as a number of basic reflective and transmissive material models. Indeed, for lots of basic hard surface material types, we will probably find that we don't have to go much beyond these base phenomenon components in order to get what we want. For the times when we do need extra levels of control and or complexity, however, the Miele material provides a very flexible and powerful layer-based system. Supposing then we wanted to add some reflectivity to our shelf based specifically on Fresnel equations. Well, we could just switch the base component over to the reflective plastic option and handle things from there, given that this provides the ability to easily blend between the diffuse and reflective aspects of a material. For demonstration purposes though, let's do things a little differently by leaving our base component set to diffuse and instead clicking to add a Fresnel controlled glossy reflection layer. Again, what we get are very easy to work with controls, all of which are focused towards producing reflections that work according to an artist-controlled IOR value. To add something very obvious to our render, let's set the IOR here to 3.5 and the roughness value, which controls how sharp or how blurred the surface reflections will be, to a value of 0.3. Taking a render reveals that we have now successfully mixed the layered options applied to the shelf, with the mix or blend amount being controlled in this instance by the IOR setting. If we eventually decide that we don't need a layer that has been added to a material, all we have to do is simply hit the little trash can icon and we are back in this instance to just our regular diffuse material. And of course, creating the other two material types that we want is just as easy using the Miele option. In the Hypershade window then, let's click to add two more Miele materials, naming the first Miele_glass and the second Miele_metal. We can then apply the glass material to the large bowl sitting on our shelf and the metal to all of the smaller ones. For the metal material, let's set the base component to reflective anisotropic, set the glossy blend to a value of 1, so essentially no diffuse contribution, and the glossy roughness to something like 0.25. For the glass, we can set the base component to transmissive clear, and if we want something like a smoked glass look, leave the defaults just as they are. For more of a clear glass though, we would need to set the colour option here to white or something very close to it. For a physically accurate coloured glass, whereby the colour naturally deepens on thicker parts of the geometry, we would need to switch the base component to transmissive distance, set the colour, here I will choose a rich green, and set the appropriate distance for this particular piece of geometry. Something around about a value of 4 centimeters should show off the effect nicely here. If we wanted frosted glass, then roughness values of around about 0.2 to 0.6 should work well. For now, I'm going to keep things nice and clear by setting a value of 0. With all of those settings in place then, let's take a render and see what we have. Before doing that, however, in order to see the full fruits of our labours, it would probably be a good idea to go ahead and disable the final gather and photon maps that we are currently using in the scene, and instead recalculate the GI solutions with the new Miele materials in place. To do that, let's open up the Render Settings dialog, and in the Indirect Lighting tab, turn the Rebuild Photon Map option on, and then delete the current saved map name from the naming field. We then want to do essentially the same thing down in the Final Gathering map rollout. Now we're ready to go ahead and take a render. And as you can see, with the Miele material, getting really good looking final results is a very straightforward and simple thing to do. And of course, we don't have any of the extra memory and computational overhead that naturally comes when using a monolithic shader such as Mental Ray's MIA material. When working with render engines such as Mental Ray, there are certain core fundamentals regarding the technology at work that we, or more specifically our work, will certainly benefit from understanding. We have already looked a little bit in Chapter 3 at the workings of Mental Ray's GI systems, but in this particular video we want to spend a few minutes focusing on another key area of Mental Ray, this being its image sampling capabilities. The question we're going to start with then is, just what is image sampling? Well, when we talk about the image sampling process, we are, in reality, talking about the ray trace rendering process itself. You see, in order to collect all of the relevant information required from a scene, such as the shape of geometric surfaces, the properties of applied materials, lighting and shadow information, and so on, our render engine needs to somehow sample the scene so that it can determine what colour values should be drawn in the pixels that will make up our final rendered image. The million-dollar question, of course, is how will this gathering of information be accomplished? Well, this is where we need to dig a little bit into the basic workings of the already mentioned ray trace rendering process, which, generally speaking, goes like this. From the rendering camera, the engine will shoot a number of rays through an internal frame buffer that represents each of the pixels that will make up the final rendered image. These primary rays, sometimes referred to as eye or camera rays, are sent out into the 3D environment in order to trace or bounce their way through the scene, sampling or gathering information from objects found in the rendering camera's field of view as they go. As these hit or come into contact with geometric surfaces, they take note of and collect a wide range of information such as diffuse colour values, specular reflectivity levels, and so on. They also, with each hit, send out shadow rays. Their very specific job is to trace a line from the point of surface contact toward any direct light sources that may be found in the environment. These will determine whether or not that specific surface point needs to be rendered as if in direct light or in shadow. Our primary rays will also, on contact, make an evaluation as to whether or not secondary or bounced rays are now going to be required. These are needed when a surface material has properties such as reflections and or refractions in its definition. Once a user-specified amount of sampling or information gathering has been accomplished, all of the data collected up to that point gets returned back along each ray's travelled path, fed into the renderer for evaluation and averaging, and then is drawn in the render view window as a final pixel colour value. Of course, this is an extremely simplified overview of what is in reality an incredibly complex process that can potentially involve millions of rays being cast and traced through our scenes. This simple overview though is enough for us to work with for now, and so move on and take a look at the controls available when working with Mental Ray's unified image sampling engine. Over the next two videos, we're going to take a look at the controls made available for tweaking and tuning the quality of renders taken whilst making use of the unified image sampling engine. The scene we will be working with consists, as you can see, of a fairly innocuous looking setup that nevertheless presents a number of fairly typical challenges to our image sampling engine. We have, for instance, plenty of straight lines in the scene, both in terms of the materials and on the geometry itself. These, of course, can be the bane of pixel-based graphics applications. We also have on our materials both glossy and blurred reflections, noisy surface patterns, flat colour surfaces, and of course we are making use of Mental Ray's native IBL lighting in the scene, which at its default quality setting of 0.2 will throw quite a lot of shadow noise into our renders. Now whenever we start a new scene in Maya that makes use of Mental Ray as the production renderer, we will, if I just open up the render settings dialog and come into the quality tab, find ourselves working with these settings. A sampling quality value of 0.25, min and max sample rates of 1 and 100 respectively, an error cutoff of 0 and a filter type of Gauss. In fact, if I just pull up the render view window here, we can take a look at what a render of the scene would look like using these very settings. Now whilst what we get is obviously a very noisy image, it is also an extremely clear representation of just what scene lighting and materials are going to look like. We have no missing detail on our textures, even though they contain really fine line detail. We have no serious stair-stepping or jaggies, as they are sometimes called, on prominent geometry edges. We even see the fine noise detail on our worktop surface standing out very clearly indeed, with no moire patterns or any other kind of artifacting showing up. Now of course the question that we will pretty much always be asking ourselves whilst working with the default image sampling values in Mental Ray is, how can I make my render look better? Well, a typical workflow for the production of quality images when rendering in legacy mode was to set the min and max sample values to 0 and 2, so actual min and max samples of 1 and 16 respectively, and then tune the anti-aliasing contrast settings from their default of 0.1 to values in the region of 0.005 to 0.003, which were generally regarded by many artists as the production sweet spot. With unified sampling, of course, we have no such controls available to us. Instead, we have this quality slider, which essentially determines the point at which Mental Ray will stop trying to get rid of noise in the scene, with higher quality values obviously implying a desire for less noise to be present in the final image. We also have min and max sample settings. Rather than thinking in terms of jagged edges or missing pixel data, as we may have become used to when rendering in legacy sampling mode, image sampling in the unified engine, as you are perhaps already starting to guess, really comes down to the simple question of how much noise are we prepared to put up with in our final images. The available quality range on the slider starts at 0.1, which of course will give us extremely fast but very noisy draft renders, and goes all the way up to a value of 2. This field, though, like many in Maya, can of course be overdriven and so allow us to input values that are theoretically capable of eliminating pretty much all noise from an image. The recommended range for use in general production, however, sits somewhere between the 1.0 and 5.0 mark. Although once we get up to the 5.0 mark, it may also be time to think about adding a higher max samples value than the default of 100. Of course, the higher the quality settings we use here, the longer our render times are going to be, given we are essentially instructing Mental Ray to become increasingly aggressive in its attempts to seek out and eliminate noise in our image. In fact, let's move on to our next exercise, where we can go ahead and make an examination of both the render quality and render times that we can get from the system whilst working with the quality control slider. Time then to put the quality controls for Mental Ray's unified sampling engine through their paces, and in this exercise see what kind of results can be produced as we work first of all with the quality slider. To do that, we are, in Maya's render view, going to be comparing a number of pre-rendered images, each of which makes use of differing quality values. Here we are looking at essentially the render as taken from our previous exercise, which has all of the unified engine's sampling defaults in place. This, as already noted, produces a very noisy image, but one that interestingly has no missing detail or serious stair-stepping present on geometry edges. Let's take a look at what happens then as we increase the quality slider from its default value of 0.25 to what I will call a minimum production quality setting of 1. Well, the level of noise cleanup in the image is pretty obvious. The wall behind the glass door, the interior sections of the cupboard, and the countertop down at the bottom of our render all show very clear levels of noise reduction. Of course, now we see our render time starting to climb, because whereas the previous 960 by 1200 pixel render took around about 5 minutes to complete, this time we are at the 9-minute mark. Let's make the jump to a much higher production quality setting now and enter a value of 5 into the slider's numeric field. Now, although this time as we look at the render produced, the quality jump is not quite so obvious as previously, it is nevertheless still readily discernible as we make a comparison between the two images, particularly so if we zoom in and look a little more closely at the noise seen on our geometry. At these quality levels, of course, the render times have also jumped quite dramatically, as we are now at 22 minutes plus for this render. Clearly, the choices we make regarding our image sampling quality settings comes down to the simple balancing act of how much time we want a frame to render for versus how much noise we are prepared to put up with in our image. Now, besides the quality slider and samples per pixel controls in the quality tab, we also of course have these filter options that, when used with the older legacy sampling mode, could make quite a noticeable difference to the look of a final render. For the sake of completeness then, let's take a look at utilising these options with the unified engine using our minimum production quality slider setting of 1. The default filter option of Gauss, along also with Box, are the softest or blurriest of the filter types available in Mental Ray, which oftentimes makes them especially useful on animated sequences, given that the softening they produce can help reduce or even eliminate the sparkling or scintillating textures. My personal general use favourite in the filter types has always been Triangle. This is because it sits nicely in the middle of the blur to sharpen filter range, and so oftentimes has provided a best of both worlds option. Indeed, if I switch between renders here, we can see the obvious sharpening effect that now takes place, although we do need to notice that the noise present in the scene also gets sharpened in the render, which is something we may need to think carefully about when it comes time to make our choice of quality settings and filter type. In fact, if I go ahead and take a look at the Lanczos render, which is the sharpest of the filter types available in Mental Ray, you can see that pretty much all we get here is a shifting around of the noise. Now, if it is that we're going to be applying any kind of post-production effects to our renders in applications such as Photoshop or After Effects, then we may well want to avoid baking this level of sharpening into the renders that come out of Mental Ray, seeing as we can instead apply sharpening as a post effect where we can dial the strength up or down as much as we please. Now, of course, there are other sample settings in Mental Ray that will affect the final quality of our renders. For instance, material-based samples such as those used for blurred reflections, shadow samples seen on soft-edged or area shadows, the IBL skylight with its shadow quality setting. All of these, where they exist in a scene, will need to be set at reasonable and balanced sampling levels if we're to get the best possible speed to quality ratio from our Mental Ray renders. Indeed, one way that we can go about accomplishing this is to make use of Unified Sampling's diagnostic tool, which gives us the ability to check sample distribution in the scene. In our next exercise then, we will take a look at how we go about creating a diagnostics render whilst using the Unified Sampling engine. Many existing users of Mental Ray have, over the years, developed a working pipeline that includes making use of Mental Ray's diagnostic tools as a means of figuring out just where in a scene the majority of image samples are being used. This of course is a brilliant way to fine-tune our render settings. In this video then, given that outputting a diagnostic whilst using the unified sampling engine is a bit of a different process as compared to using legacy sampling mode, we want to quickly run through the steps required. Indeed, what we are going to do here is generate a floating point EXR file that actually contains a wealth of diagnostic information, all of which, as we say, can be used to tweak and fine-tune our final render settings. To go ahead and generate this diagnostic frame buffer, the first thing we will need to do is ensure that we are actually rendering with the unified sampling engine from inside the render settings quality tab. Once we are sure of that, we can come down to the sample options rollout and put a check in the diagnose samples box. Now, in terms of setup, that really is pretty much it. We will of course need to set the sampling level that we want to use here, so a value of 1 on the quality slider should work just fine for now, and then we can go ahead and take a render. Now whilst it may at first appear as if nothing more than a standard render has been produced here, if I just open up the render view file menu, come down to load render pass, and then click on the diagnose samples option, you can see that what we get is a diagnostic.exr file that opens up in NVIDIA's InfDisp application. Now you may be wondering why we are looking at this image, as all we appear to be seeing is a strangely coloured version of the render that we can already see in Maya's render view. Well, first appearances can indeed be deceptive, because if I open up the layer menu here, you can see that we have access to a number of diagnostic layers, each of which contains a specific type of diagnostic data. As we are currently interested in our image sampling rates, let's select the buffer samples layer and see what we get. Well, what we appear to have is a completely white image. The problem here is that the exposure values at work in the scene are masking the sampling data that is in fact contained inside this image. To rectify this, all we need to do is dial down the exposure value on the UI here. Something around about -5 should cause everything to come nicely into view. Lighter portions of the image that we now see denote areas in the scene where higher levels of image sampling are being used. Darker areas show the use of less samples, whilst the darkest portions represent areas where the bare minimum number of samples available have been used. If we want or need sampling information that is a little more precise than this simple visual evaluation, we can hover our mouse cursor over the image and notice that down at the bottom of the InfDisp UI we get a readout that tells us, amongst other things, the exact number of image samples being used on a pixel by pixel basis. Indeed, as we roll over the values here, we may quickly come to discern that our current quality setting isn't actually making use of the maximum number of samples allowed in this scene, which of course is the unified default of 100. We can also see that some of the flatter areas, the back of the cupboard for instance, are only making use of fairly low sampling rates. Now both of these pieces of information could suggest that we may want to push our quality slider up a little in order to force a more aggressive level of sampling from the system. No matter what we are rendering then, the ability to quickly and easily output a diagnostics image that we can then scrutinise in order to help fine-tune the rendering of our scene will always be an extremely handy piece of functionality to have access to. Although generally recognised as a render-intensive process, in-scene or in-camera motion blur in a 3D application can sometimes be the best, maybe even the only way to create some very specific looks on moving objects in a shot. In this video then, we're going to focus on using Mental Ray's motion blur tools and hopefully demonstrate just how easy creating this effect can be. In our scene here, if I just hit the play button, you can see that we have some basic animation in the form of a bait dynamics simulation. This provides us with some base motion in the scene onto which we can now add a motion blur effect. If I just reset the timeline and then come to the panels menu, you can see that we have a number of cameras set up in the scene, 3 of which have had the mblur tag added to their name. These, as you will have guessed, have been set up to help us test our motion blur effect. If I just select the 01 camera from the list, you can see as I scrub the timeline at the beginning of the animation here that we have motion on our pool cue as it weighs up where to strike the cue bar. Let's set the timeline at frame 44 and then take a render. Clearly, even though there is considerable motion going through this frame, camera 01 is currently capturing no motion blur at all. In order to turn on and then work with Mental Ray's motion blur feature, let's open up the render settings dialog and in the quality tab come down to the motion blur rollout, and from the drop down choose either no deformation or full in order to turn motion blur on for the scene. In this instance, full will do fine. Mental Ray will now use this motion blur by parameter to control the amount of motion blur generated by or applied to moving objects inside the camera's field of view. To create a fairly typical, although to my eye somewhat exaggerated looking blur effect, we can leave all of the defaults just as they are. For me personally, however, a value of 0.2 in the motion blur by field will give us an effect that is a little more visually interesting, so let's go ahead and apply that instead. Motion steps are a way of cleaning up the blur effect. Larger values result in smoother motion blur, coming of course at the cost of higher render times. We do also need to keep in mind that the image sampling values we use in our final render settings will themselves affect the quality or smoothness of any motion blur produced, and so we would do well to check that we are happy with those settings before perhaps unnecessarily increasing the number of motion steps being used here. Typically speaking, even when using only the default motion steps value of 1, rendering with the unified sampling engine produces much faster and much cleaner end results as compared to the legacy sampling mode that is. With everything set as we want it for this shot then, let's go ahead and take another render. What we ultimately get is a very nice motion blur effect that is in fact fairly noise free to say that we are rendering using only a sampling quality and motion steps value of 1 here. There is a penalty to pay in terms of render times for the motion blur effect of course, but if what we really need in our shot is genuine in-camera motion blur, then the final results will generally make the wait worthwhile. If instead of moving objects we have a moving camera in our scene, you'll be glad to know that there are no extra steps that need to be taken in order to create full frame motion blur in Mental Ray. The engine will simply go ahead and calculate this for us using the current motion blur settings with no problem at all. Motion blur then is a great way to add implied motion to objects that we are capturing in still frame, or indeed to add more realism to the motion of objects in an animated sequence. Using the Mental Ray controls, as we have seen here, really is a piece of cake. In fact, given that we already have a number of extra motion blur cameras set up to capture various portions of the simulated motion here, feel free to go ahead and experiment with the motion blur settings by taking some extra renders of your own. When it comes to adding a photographic depth of field effect to our renders, there are in fact a number of options available to us whilst working with the Mental Ray engine in mind. In this video, we're going to focus on the main UI controls available for creating genuine in-scene depth of field whilst rendering with a Maya camera. As we already have a dedicated depth of field camera positioned in the scene, let's jump into that by coming to the Panels menu and from the Perspective flyout choosing the Cam_DOF option. As we need access to our camera's control parameters, let's make certain that it is selected. And then over in the Attribute Editor, take a look at the depth of field controls found, naturally enough, in the depth of field rollout. As you can see, the depth of field control mechanisms in Mental Ray really couldn't be simpler. We have a checkbox to enable and disable the effect, which we of course want enabled for this exercise. We have a focus distance that sets the point of focus in the scene, in other words the portion of the scene that we won't be blurring. We have an f-stop value that controls how deep or how shallow the depth of field effect in the render will be. And then finally we have a focus region scale that essentially acts as a scale factor for the focus distance value, irrespective of the current f-stop setting. Now there are also a couple of ways that we could go about determining the depth of field values that we want to use here. How we go about doing that will really depend on the strength of depth of field effect that we are wanting to apply to our renders. One quick and easy way to get a usable focus distance value is to select an object that is somewhere around about the centre of the zone that we want to be in focus, so let's say our cue ball here, come to the Display menu, and then from the Heads Up flyout choose Object Details. This gives us an in-viewport display that tells us, amongst other things, the distance of this particular object from the viewing camera, 154.4 centimeters in this instance. Let's reselect our rendering camera then and apply that value to the depth of field focus distance parameter. What we see in the viewport, which is a nice aspect of using these depth of field controls in conjunction with viewport 2.0, is a preview showing us a soft depth of field effect on the pool ball sitting closest to the camera, whilst up at the top of the table the cue ball that we picked as our point of focus has remained pretty sharp looking. How strong or how weak the depth of field effect will be, so in other words how much blurring will be applied to defocused areas of the image, will depend entirely on the f-stop setting that we use here. In fact, let's take a render of what we have and see how close the viewport preview gets to the final rendered effect. Well, the answer to that question would be pretty close indeed. The cue ball at the far end of the table looks nice and sharp, whilst the ball sitting closest to the camera show that a fairly subtle blur effect has been applied to them. To deepen the focus depth and so make the effect here even subtler, which oftentimes is the best way in which to make use of depth of field, we can increase our f-stop number to 8 and then see what we get from another render, which in the end is pretty much the effect that I was after. We could even of course easily flip the effect that we have here by setting a focus distance of about 32 centimeters and of course rendering again. Now, although the quality of the render here is pretty good, should we want or need to create an even cleaner or smoother looking final render, all we would really need to do is increase the quality of our image sampling settings. Do be warned though that any kind of significant increase to the quality settings, especially when used in conjunction with depth of field, will probably impact our render times quite noticeably. I'm sure you will agree though that using Mental Ray's depth of field controls really couldn't be simpler. All we need to do is set the point of focus for our shot using the focus distance value, set the depth of focus for our shot using the f-stop value, and then simply render away. Caustic lighting effects can be seen pretty much everywhere in the world around us. In fact, oftentimes they become such a familiar and expected sight that we don't always notice they're there. For instance, not many of us take the time to stand and watch as focused light patterns create a dazzling light display as we fill a bathtub, and yet they are there because caustics are just a natural part of the way that light behaves. Of course, this naturally occurring real-world lighting effect doesn't show up by default inside a CG lighting setup. Typically speaking, we have to deliberately enable caustics and then work with a distinct set of controls in order to tweak and tune the effect, which of course is exactly what we are going to be doing over the course of our next two videos. What we have in our test scene here are essentially the building blocks from which we can create a caustic lighting effect. We have a strong directional light source in the form of a Mental Ray physical sun. We have a suitable piece of geometry in the form of our butterfly ornament, to which we have also applied a refractive material, namely glass. As things stand then, we would probably expect to see caustics generated once we have enabled them in the scene, that is. Before we go ahead and do that, however, I just want to tweak our scene setup a little so as to speed up the test renders that will be needed here. Firstly, from either the viewport or the outliner, let's select only the scene elements that are absolutely essential to the creation of our caustic effect, these being the foreground butterfly and plinth geometries, along of course with our sun direction node. Once we have them, we can come to the display menu and hide our unselected geometry. This means we can now perform faster test renders using, as we say, only the elements in the scene that are really necessary. Let's also have our geometry stand out quite prominently in those tests by setting it to be rendered against a black background. Of course, the problem we have here is that if I just select our camera, grab focus on the physical sky node, and then simply turn the physical sky environment off, we will not only end up losing our sky lighting here, but also the reflections on our glass object that are critical to its finished look, given of course that we have already hidden the rest of our scene geometry and so have a reflective object sitting in just a black environment. Thankfully, we can use a little bit of Mental Ray functionality that we have already looked at earlier in the course in order to help us get around this problem, which is to enable the Use Background function on our physical sky. This time, however, we won't assign a map or image to the background slot. If I then go ahead and take a test render, we can see that what we get is really quick feedback from the render and with all of our scene reflections still in place. Our next step is to optimize our direct light's positioning in the scene in order to make it as efficient as possible when it comes to generating our caustic photons. Now obviously, if we have carefully set up the lighting for our shot, the last thing we will want to do now is disturb or spoil that setup, which isn't a problem as changing the positional information for our direct light won't affect current scene lighting in any way at all. The first thing we want to do then is select the sun direction node in the outliner, and then in the viewport panels menu choose the look through selected option. Now seeing as we are wanting to look through our direct light here as if through a normal Maya camera, let's go ahead and pull up the camera options, and then from the orthographic views rollout uncheck the orthographic option. What we are able to do now from the viewport's view menu is use the frame all command, which will nicely reposition our sun in the scene, focusing it on our butterfly geometry. Because this move hasn't altered our direct light's orientation in any way though, the original lighting that we had set up in the scene has been left completely intact. In fact, let's jump back into our caustics camera view, save our earlier render, and then take a new one just to make certain that what I am saying here is correct. Once done, a quick flick between the two renders shows that both lighting and shadows have remained completely untouched. Finally, as we clearly have no caustics effect present in our renders as of yet, we can go ahead and enable caustic photons in the scene by opening up the render settings dialog, coming into the indirect lighting tab, and then in the caustics rollout putting a check in the caustics option that we see there. Now if I go ahead and save the current image and then hit the render button again, we will quickly see that enabling caustics and actually getting them to appear in the scene can oftentimes be two very different things. The simple truth is that there are a number of very specific steps that have yet to be taken in order for us to generate and render caustics with mental ray, which we will of course take a look at doing in our very next exercise. Although we have in our previous exercise run through some essential scene setup in order to optimize for caustic generation and have also enabled caustics in the render settings dialog, we still, if you recall, are not getting any kind of caustic effect being generated in our scene. This means that we still have a little bit more work to do before we get the effect that we are after. To work through the necessary steps, let's first of all select our butterfly geometry and in the attribute editor access its material parameters. Now if we open up the advanced refraction rollout here, we can see down at the bottom that we have both refractive caustic and transparent shadow options, with the latter being the option currently in use. This MIA material default has been set up to prevent unnecessary slowdowns in our renders. Slowdowns that could be caused by the render engine automatically producing or calculating effects that we neither want nor need for a shot. Rather than automatically adding the computationally expensive caustics then, the MIA material instead gives us a fairly nice looking transparent shadow effect. In this instance though, we are going to want to specifically enable the refractive caustic option. With a caustic creating material setup, the next thing we need is to ensure that we have a photon emitting light source in the scene. To do that, let's select the sun direction node from the outliner and then jump into the caustic and global illumination rollout over in the attribute editor, where we can put a check in the emit photons option. Now typically speaking, all that should be left for us to do is hit the render button. If we did that, however, we still wouldn't see any caustics being generated in our scene. This is because with the MIA physical sun shader attached to our directional light, we have just one more step that we need to take, a bit of a workaround really, which sees us in the custom shaders rollout of the light source, right click on the photon emitter slot and use the break connection command. This means that we can now make use of the light object's own photon intensity controls instead. With that done, if I again take another test render, we can see that we are most definitely now getting caustics in our scene, an effect that is currently way too strong to be of any real use to us. Back in the caustic and global illumination rollout then, let's set the intensity for the caustic photons at a value of about 150 and again see how that looks. Well, whilst we have certainly brought our caustic effect into a much more usable range, the whole thing is looking a little too soft for my liking. Let's sharpen things up by first of all increasing the number of photons being generated. Something like 1 million should do nicely. We can then add a little more sharpness to them by coming into the render settings dialog, dropping the photon accuracy value down to something like 40, and then finally switching the filter type over to cone. We're now ready to take a final render. Working with caustics will of course always require a measure of trial and error. The values needed to get caustics working and working well will always be very much scene specific, dependent as the effect is on the light types, geometry and material settings that we are using in our scene. Still, the basics that we have looked at over the past 2 videos should be more than enough to get us up and running with creating caustic effects of our own. Whilst bump mapping is a material effect that can work well in many instances, creating as it does the illusion of depth in an object without adding anything to our overall render times, there will be occasions where the fact that this is a render engine trick becomes a little too obvious for the success of the shot. On such occasions, especially where the believability of a material or object is integral to the success of the project, we may want to swap bump mapping for displacement mapping. One extremely nice feature that Mental Ray shares in common with many ray trace render engines available for Maya is its ability to generate render time displacement based on grayscale inputs. This means that rather than having to process extremely dense meshes in the viewport whilst we work, we can postpone all of the heavy mesh subdivision required for good displacement until we actually hit the render button. To make a start at creating our displacement effect, let's take an initial render of our scene, so as to have something against which we can make progress comparisons as we go. The first thing we want to take note of in the render, if I just zoom in here, is the fact that the outline of our egg geometry is, in and of itself, perfectly smooth. No real breakup or irregularities at all, other than the natural polygon outlines that we are seeing, even though we do have small surface detail being provided by means of a bump map in the material. To change this behaviour and add breakup to the surface, let's open up the Hypershade window, where the first thing we need to do is come into the Materials tab, select the egg material, and then from up on the toolbar, click to graph both the incoming and outgoing connections for it. Next, we need to create the network that we will be using in order to actually displace our egg geometry. So, with the Shading Group node selected, let's, in the Shading Group Attributes rollout, click to add a control map to the displacement mapped slot. In the file node for the displacement flow, seeing as we are wanting to use a grayscale bitmap to control our displacement, let's click to add our grayscale egg displacement map. If we now draw a region around our egg inside the render view window and then take another render, we can see that we do indeed have displacement working. Now, whilst that statement may be true, we can also see that we are in need of adding a little bit of finessing to the displacement effect in order to achieve a quality end result. One obvious problem that we have, if I just scrub to compare with the non-displaced render here, is the fact that our geometry has somewhat ballooned in size, which in this instance is not really the effect that we're after. This inflation of the geometry happens because in Mental Ray, every non-black pixel found inside a displacement control map pushes the mesh outward. As you saw when we added the control map to our shader network, the vast majority of pixels in this particular control image are indeed non-black. To dial down the strength at which our displacement map is being applied then, let's jump into the colour balance rollout for the file node and set the alpha gain value to around about 0.375. We need to do this because Maya typically connects file textures being used for bump and displacement mapping via their alpha attribute. With the alpha is luminance option enabled, however, Maya will instead use the intensity or luminance values of pixels found in the RGB image to create the effect. It is still, however, the alpha gain value that will control the intensity of those pixels as applied to the bump or displacement effect. Saving the image we already have in render view and then rendering again reveals that we now have a much more acceptable level of displacement. Of course, things are still in need of some tweaking here, as I really want to create a somewhat smoother, cleaner looking final result. which is why at this point we're going to move on to our next exercise, where we will add a mental ray displacement tessellation approximation node to our egg geometry in order to refine and clean up the displacement effect that we're getting. Although we have so far in our displacement exercise managed to create a render time displacement effect, we will, in most instances, want to exercise finer control over the displacement than we are currently getting. So, in this video, we're going to demonstrate how we can go about using some mental ray specific controls to tweak and refine the displacement that we're seeing. Specifically, we want to add a mental ray displacement tessellation approximation node to our egg geometry, which is a complicated sounding name for what is in reality a fairly straightforward process that will add render time subdivision or tessellation to our geometry. With our egg selected then, let's come to the menu system and choose Window, Rendering Editors, Mental Ray, and from there open up the Approximation Editor window. What we want to do inside here, again making certain that our egg geometry is indeed selected, is click to create a displacement tessellation approximation surface. Now whilst we could, over in the attribute editor, work with pretty much any of the approximation methods made available to us, for ease of use I'm going to choose the spatial method here, set the maximum number of subdivisions allowed inside the displacement effect to 6, and then finally set the length value to 0.02 and check the view dependent option. The length value here is used to determine the maximum allowed size of an edge inside the displacement effect. The smaller the edges allowed, the finer the displacement effect can be. And by default, this value is measured in scene units. With the view dependent option checked, however, they are measured instead in pixels, which of course naturally means that the further an object is away from the rendering camera, the less subdivision it will have applied to its surface. With those settings in place then, let's take a render in order to see what we have. Clearly, the result we see reveals a much refined and smoother displacement effect, and if I just zoom in quite a way in the render view window, we can indeed see that, unlike at the start of our exercise, the geometry profile is no longer completely smooth and unbroken. Because of the detail contained in the grayscale map, we are seeing definite pits and breakup in the geometry outline, which certainly makes this a much more believable object, especially so when the rendering camera is set this close. And we could of course push the effect or strength of the displacement by increasing the alpha gain value on the grayscale map file node if we so desired. Finally, I also want to use our grayscale displacement map here to add one more effect to the finished render, which is to dial down the reflectivity of our material in areas where the displacement creates these depressions. To do that in the Hypershade editor, let's middle mouse click and drag on our displacement input file node and drop it onto the egg MIA material, making certain to connect it up to the material's reflection colour port. The final render reveals that we do indeed now have a very nice looking final displacement effect. Whilst of course bump mapping, wherever possible, is going to be the preferred option for adding detail to a surface from a memory and render speed point of view, that is, on occasions where the level of realism required in our objects and or materials is critical to the success of a project, we may find that the use of displacement mapping becomes an absolute must. One of the most frustrating moments on any rendering project comes when, after many minutes, maybe even hours worth of intensive CPU calculation, that the application we're working in suddenly crashes with an out-of-memory error. Now of course, as projects in all aspects of the 3D industry grow larger, with more and more data being loaded into scenes, the potential for this painful scenario to be encountered on a fairly regular basis continues to grow. Any tools then put at our disposal by software developers to help combat this problem are going to be most welcome indeed. One such being the introduction to pretty much all modern render engines of the proxy object. A proxy in mental ray terms is a visually simplified piece of geometry that sits in the scene as a stand-in for a much more complex, sometimes even extremely complex object that in and of itself would be difficult to make use of in a render due to the strain it would place on system resources. This strain can occur because, by default, ray trace render engines such as Mental Ray need to have all geometry and textures for a scene loaded into memory. Now, Mental Ray can, using the default BSP2 ray trace acceleration method, flush memory when necessary. This, however, may not necessarily be enough to allow Mental Ray to render scenes populated with large amounts of dense polygon data. Now, whilst with this scene we aren't on any reasonable machine going to run into this kind of problem, we do nevertheless have an extremely dense mesh object in here in the form of our character's hair, which, when selected, is confirmed by the viewport stats as adding almost 1.5 million tries to the scene all by itself. Imagine if we had a crowd of these objects in here, things could definitely start to get tricky from a rendering point of view. In a situation like this then, it makes perfect sense for us to turn our character's hair into a render proxy object. Now, one thing we do need to consider before we go ahead and turn geometry into a proxy is the fact that once done, the model will no longer be modifiable by us in the scene. This is a one-way trip, and so we need to be certain that the model is completely finished before we go ahead. That having been said, however, there are some good workflow habits that we may want to embrace if we find ourselves creating proxy objects on a regular basis. One of which would be to always save a copy of the soon-to-be proxy geometry to disk. We could, for instance, with our hair here selected, come to the File menu and use the Export Selection option. This lets us save a selected object to its own Maya file, meaning we could return to the base geometry and modify it at any time should we have a real need to. Of course, as what we really want to do here is take a look at how we go about creating a render proxy in the scene, let's, while still inside the Export Selection dialog, access the Files of Type drop-down, and rather than saving to a Maya scene file, let's this time choose the Mental Ray output option instead. This gives us the ability, in the Options panel, to make certain that the selection output type is set to Render Proxy Assembly. Now, everything here I will leave at default and go ahead and give the file a name, so proxy_hair, set the output folder to Render Data and Mental Ray, and finally go ahead and click Export Selection. Now, in a typical render proxy workflow, we would at this point probably go ahead and create a simple piece of standing geometry in the scene, such as a cube or a sphere, align it to our hair geometry, and then go ahead and delete the hair mesh from the scene, as from a rendering point of view we actually no longer need it. However, in order to save a bit of time here, I'm just going to show how we can in fact load the render proxy back into the scene using it to replace the hair geometry from which we have just created it. Now, whilst this, as I say, is not a typical render proxy workflow, it is nevertheless one that will actually cut down on both our memory requirements and render times for the scene, although it won't of course lighten the polygon load on our viewport, which the aforementioned typical render proxy workflow would. To use our proxy then, with the geometry we want to replace at render time selected, let's, in the attribute editor, make certain that we are in the Shape tab, and then open up the Mental Ray rollout file now. In the render proxy slot, let's navigate to the folder where we saved our proxy file, namely Render Data and Mental Ray, and then click to load the .mi proxy file. And that really is it. All we need to do now is hit render, and Mental Ray will go ahead and use the much more memory efficient proxy file at render time as opposed to the memory expensive polygon hair mesh, with the final result, as you can see in the render view window, looking just fine indeed. Although we have come to the end of our up and running with Mental Ray in Maya course, your education as a render artist certainly doesn't stop here, especially so given that raylinda.com offers lots of great courses that can help you continue to grow your lighting, texturing and rendering skills. As mentioned in our introductory chapter, given the photographic nature of the tools found inside render engines such as Mental Ray these days, many of the photography courses found in the online library can be extremely useful, especially ones such as Ben Long's Foundations of Photography series, with the exposure, composition and lenses courses being particularly useful. There are also lots of online resources connected to the Mental Ray renderer, with special mention going to NVIDIA's own nvidia-arc.com website. Here, in the Mental Ray section, we can get info on the latest updates to the Mental Ray engine, as well as having the option to join NVIDIA's Advanced Rendering Forum, which has a section of course dedicated to Mental Ray. One learning resource you could make good use of would be the exercise files download provided with this course. We have very deliberately used a variety of lighting and exposure setups in these files to demonstrate the diverse approaches that can be used. A lot can be learned from simply picking apart working scene files and maybe even observing how changes you make to them affect the resulting renders. Ultimately, the learning approach I would encourage the most is that of getting as much practice using the Mental Ray engine as possible. The more familiar we become with the way in which its materials, lights, GI systems, etc. work, the more productive and creative we can be with them. Finally, I would just like to thank you for taking the time to work through this course with me and hope that it has given you at least some of the knowledge you need in order to start creating your own works of Mental Ray rendered art. My name is